Okay, welcome everybody. So in this video, I want to build off of this previous example that we looked at where we had a vector space R3 with usual scalar multiplication, but we defined addition in some weird non-standard way, which violated some of these properties. So we had an addition operation which violated the conditions for a vector space. And one bad thing that came out of this is in as far as identifying whether or not there is a zero vector in this vector space. The problem here is that we don't have a unique zero vector. So if I take any vector u in R3 that I'll denote u1, u2, u3, probably would like to think about the zero vector as being the vector of all zeros. And this would indeed give us the original vector u back. However, there are other vectors that we could pick, right? I could take u1, u2, u3, and add to it the vector 1, 0, 5, for example, and that would also give me u back because as far as this addition is concerned, I'm adding 0 to each of these positions. So having a zero vector, having multiple zero vectors is going to be an issue, particularly when we want to come down and then define the additive inverse, which depends on how we define the zero vector. So what I want to show you on the next slide is that by satisfying all of these properties for a vector space, for vector spaces, we'll see that both the additive inverse and the zero vector are unique. So we'll take a look at this on the next slide because we've run out of space here. But yes, keep this in mind that this was an example of something that was not a vector space, and this is why it was possible that we had more than one zero vector in this setting. But in cases where all of these axioms are satisfied, we'll see that it will not be possible to have more than one different type of zero vector. Okay, so now let's prove this claim that I was making on the previous slide more generally. So if V is a vector space, so this means we have V, we have some addition of objects within V defined, and we have multiplication of objects in V by a scalar as defined operations. And we're going to assume that they satisfy all 10 of those axioms. If that is the case, then there's going to exist a unique zero vector that we'll denote with this bold 0. Okay, so let's take some vector w, which is in V, and let's say that it satisfies the property that a zero vector has, namely that u plus this vector w is going to give us the vector u for all vectors u in this vector space V. So let's see what happens under this assumption if, for example, we let u equal the zero vector. Well, then that would tell us that we have 0 plus w, and we know that 0 plus w, that is going to equal, if w is the zero vector, then u plus w should equal u no matter what. So here the u is equal to 0, so u plus w should equal u, right, which is the zero vector in this case. Great. We also know that since V is a vector space, that addition is commutative. So taking u plus w, if that equals u, then adding these vectors u and w in the opposite order should give me the same thing. So namely, if I take w plus u, which again, we're setting u equal to the zero vector, then when I switch this order around, w plus the zero vector should also give me the zero vector. And so now we can see from these equations, therefore, that this vector that we call w must equal the zero vector. So therefore, the zero vector is unique. There's only one such vector so that when we add it to every other vector u, we get u back. And similarly, we get a nice property that you can verify. I won't do this in this video, but this would be a good exercise. And that is, if V is a vector space, then for each vector u in V, there exists an additive inverse. We know that because V is a vector space, but by these other properties, we can show that the additive inverse that we denote minus u is unique. So there's only one such vector that we denote minus u. so that when I add it to U, I get the 0 vector back.